First, let us take a quick look at the commands used for plotting the ACF and PACF in R. As discussed in previous tutorials, the ACF and PACF plots play an important role in determining the order of ARIMA and SARIMA models. The commands shown here can be used to plot the ACF and PACF of a time series Y. The option of lag.max is used to specify the number of lags to estimate and plot in ACF and PACF. It is important to note here that Y can be the original series or the transformed series. For instance, we can input the first difference series here to obtain the ACF and PACF at the first difference of Y. To illustrate the application of ARIMA and SARIMA models, we will consider the airline data used by Box and Jenkins. It is a monthly dataset of airline passengers from 1949 to 1960. Because it is a monthly dataset, we know that the length of the seasonal period, or S, will be 12. In our example, we will use the log values of the data. The first plot here shows the logged time series, which is not stationary because we can see a clear seasonal pattern and trend. Using the rules we discussed in previous tutorials, we can decide the order of ARIMA or SARIMA models with the help of ACF and PACF plots. If we take the first non-seasonal difference, the time series still doesn't look stationary because we can clearly see a seasonal pattern. Moreover, the ACF plot at first non-seasonal difference also shows clear spikes at seasonal lags. The value of ACF at the first seasonal lag is quite high as well. This suggests that we need to take a seasonal difference instead of a non-seasonal difference. After taking the first seasonal difference, we no longer see a seasonal pattern in the series. Also, the ACF are no longer significant at seasonal lags. The ACF at first seasonal lag is now close to -0.5, which indicates that seasonal overdifference should not be a problem. However, the time series still does not look stationary. Instead, it looks more like a random walk process. In the ACF plot, we can still see the ACF declining gradually when we look at the initial lags. Moreover, the ACF at first lag is quite high as well. This indicates that taking the first difference could be helpful. Therefore, we now also take the first non-seasonal difference after taking the first seasonal difference. The time series now looks to be stationary and overdifferencing does not seem to be a problem because the ACF at lag 1 is not close to -0.5. Therefore, we have determined that the order of capital D is 1 and D is 1. Now, we can use the ACF and PACF plots to decide the order of AR and MA lags. If we look at the ACF at first seasonal lag, it is negative, indicating mild overdifferencing. This can be accounted for with the help of a seasonal MA lag, that is, capital Q is equal to 1. We don't need a seasonal AR term, so capital P is equal to 0. Similarly, the ACF at lag 1 also shows mild overdifferencing because the ACF is negative. Again, we can use a non-seasonal MA term to account for that, and Q is equal to 1. We don't need a non-seasonal AR term, so ρ is equal to 0. Hence, we have determined the order of the SARIMA model to be 0, 1, 1 by 0, 1, 1. In R, we can use the ARIMA function provided by the stats package to estimate ARIMA and SARIMA models. This function provides all the essential options needed to estimate the ARIMA and SARIMA models. To illustrate the use of this function, we have estimated the SARIMA 0, 1, 1 by 0, 1, 1 in the command shown here. In the earlier part of this tutorial, we determined that this order of the SARIMA model seems to be appropriate for the data. Here, Y contains the logged time series variable that we are using. The order option is used to specify the non-seasonal ARIMA order, that is, the ρ, D and Q are specified here. When we are estimating an ARIMA model, we can specify the order of integration, order of AR and MA lags here. Even if we are estimating a SARIMA model, we specify the order of non-seasonal terms of ρ, D and Q here. In our example, this order is 0, 1, 1 because we are using no AR terms, first non-seasonal difference and 1 MA lag. the seasonal option is used to specify the seasonal part of the SARIMA model. The order of the seasonal part and length of the period are entered as a list here. First, we mention the order of seasonal part, that is, capital P, D, and Q. In our example, we decided to include no seasonal AR terms, one seasonal difference, and one seasonal MA term. Since we are dealing with monthly data, the length of the seasonal period is equal to 12 as mentioned here. To estimate a non-seasonal ARIMA model, we can simply choose to not specify this seasonal option. There are several other options that can be specified in this function. One of the most useful ones is the include.mean option. We have specified it as false because we don't need a constant in the model. To include a constant, this option has to be specified as true. The xreg option can be used to specify other variables to be considered in the model. Therefore, we can use this option to estimate the ARIMA and SARIMA models with exogenous variables and a structural component. The forecast package in ARIMA provides an extremely useful function known as the Auto-ARIMA function. This function uses information criteria such as AIC and BIC to choose the order of ARIMA and SARIMA models. This function conducts a grid search of different ARIMA and SARIMA models based on the parameters and options we specify. Then, it chooses the best model based on the value of information criteria. We have the option of choosing between AIC, BIC, or AICC here. Let us consider the command shown here where y is the time series variable we are considering. The option trace is equal to true is used to show the information on different ARIMA model orders that are considered and their information criteria. The IC option is used to specify the information criteria that we want to consider. For example, we specified AIC or ACIC's information criteria. The option stationary is equal to true is specified if we only want to consider models that are stationary. The option test is used to mention the unit root test to be used. For instance, we mentioned the ADF test here for illustration. Similar to the ARIMA function, we also have the xreg option to specify any exogenous variables in the model. The option stepwise is equal to false means that the function will search over all the possible models based on the options chosen. This can take some time in the case of SARIMA models, so we also have the option to specify true here. Then the search will be faster, however, the function will skip some possible models of different orders. If we specify seasonal is equal to false, then the function will only search for non-seasonal models. The SARIMA specifications will not be considered in this case. Apart from these, there are several other options that are available in this function. For example, we can also specify the starting points and the maximum orders of row, D, Q, capital P, capital D, and capital Q that we want to consider. In Stata, we can use the ARIMA function to estimate both ARIMA and SARIMA models. To illustrate the use of this function, let us consider the same SARIMA 0, 1, 1 by 0, 1, 1 model with the monthly data we considered earlier. If we look at the command shown here, we can specify the order of non-seasonal ARIMA terms using the ARIMA option. In our example, we will specify 0, 1, 1 here because we have no AR terms, first non-seasonal difference, and one MA term. Similarly, we can specify the order of seasonal terms using the SARIMA option as shown here. Again, we specify 0, 1, 1 in this option because we have no seasonal AR terms, first seasonal difference, and one seasonal MA term. The term 12 implies the length of the seasonal period because we are dealing with monthly data. In addition to this, the option of no constant is specified because we don't want to include a constant in the model. We can also estimate this same model with a slightly different command. If we look at the command shown here, it gives us an alternative method of estimating ARIMA and SARIMA models. Here, we have used the option MA1 to specify the one moving average lag. If we wanted to include a non-seasonal AR term, we can do that using the AR1 option. Similarly, we have used the MMA1-12 option to specify the seasonal multiplicative moving average term. We can also include a seasonal multiplicative AR term using the option MAR if needed. As for the seasonal and non-seasonal differences, we have mentioned that directly with the variable. Here, S12 means a seasonal difference of length 12 periods and D implies a first non-seasonal difference. The no constant option works the same as in the earlier command. This function will give us an identical SARIMA model that we estimated with the earlier command. This second alternative of estimating ARIMA and SARIMA models gives us more flexibility with the specification. This is because we can even model multiple seasonalities using this syntax, as we can repeat the MMA and MAR options more than once. Moreover, this gives us more flexibility in terms of lag specifications because we can handpick any lags we want to include in the model. To illustrate this, let us take a look at a hypothetical SARIMA model. Here, we have taken a seasonal difference of length 12 and another seasonal difference of length of 4 time periods. If we look at the options of MAR or seasonal multiplicative AR terms, we can see two different types of seasonal AR terms. First, we have specified the MAR1-12 option, which is followed by MAR1-4 option. Therefore, we have specified two types of seasonal AR terms with different lengths. This means that we have included two different seasonal variations in the SARIMA model. Additionally, we have specified AR1 and AR4 lags separately. We have skipped the second and third AR lag to include only the AR lags that we wanted. This type of specification is not possible with earlier syntax. Now let us take a look at the results of the SARIMA model that we estimated. We included one non-seasonal MA and one seasonal MA term in our model. The coefficients of both terms are significant at a 1% level. The coefficient of non-seasonal MA term is -0.402 and the seasonal MA term is -0.557. This means that the innovations in the previous period and the previous seasonal period innovations are significantly affecting the dependent variable. Since we modeled multiplicative seasonality using SARIMA, we can write the equation for this model as shown here. The dependent variable is the seasonally differenced and first differenced y. Then, we have the first MA lag and the first seasonal MA lag. The multiplicative part of the seasonality is represented by the term here. This coefficient is a product of the coefficients of MA1 and seasonal MA1 terms. The most important application of ARIMA and SARIMA models is forecasting. Using dynamic forecasts, we can even forecast future values of the variable. In the R command shown here, we have used the forecast function to obtain the future values of y. Here, h is equal to 36 means that we want to estimate the forecasts for 36 periods in the future. Since we are dealing with monthly data, this implies that we are forecasting 3 years into the future. To do this in Stata, we have to first increase the length of our time series using ts_append add 36. This will add 36 time periods to our time series. Then, we can use the predict command as shown here. The option dynamic is used to specify the exact time period when we want to switch to dynamic forecasts. In our example, we have used 12 to start forecasting in the January of 1961. It is important to note here that Stata uses a different format time where January of 1960 is 0, February is 1 and so on. In this format, January 1961 will be 12. The graphs here show forecasts of two different ARIMA and SARIMA models. The first graph shows the forecasts made by a simple ARIMA 1-1-1 model. It is clear that this is not a good model because the confidence intervals are huge and the forecasts don't make much sense. This is understandable because a basic ARIMA model is inadequate in case of seasonality. The second plot shows the forecasts made by SARIMA 011 by 011 model that we decided to use in our example. The forecasts look so much better and the confidence intervals are not too big either. This clearly shows that SARIMA models are a good option for seasonal type of data. Thank you for watching, and I will see you in the next tutorial.